Okay, so today I'm going to tell you a bit about some work that I've been doing on the shutdown problem, which is roughly this problem of ensuring that artificial agents aren't going to try prevent us turning them off. So I'm going to try convince you that the problem is important. I'm going to tell you why I think philosophers have a key role to play in helping solve this problem. I'm going to tell you about some theorems that suggest that the problem is hard. I'm going to tell you about my proposed solution, and I'm going to see what you think of it. Okay, so right now, we don't really have to worry about artificial agents trying to prevent us shutting them down. And that's because the most capable agents known to us today are reinforcement learning agents like mu0, which comes out of DeepMind. And mu0, it sort of doesn't know it's an artificial agent. It's not aware of the wider world. And even if it was, all it can do is make moves on a chessboard or on an Atari game. And so for the purposes of shutdown, at least, it doesn't matter what these agents' goals are. You know, we can sort of shut them down no matter what. The concern, can I? Oh yeah, sweet. Okay, the concern is that that's not always going to be true. So, you know, one day we might be sharing the world with artificial agents that are what I call powerful, and by which I mean they can effectively interfere with our ability to shut them down. So the leading AI labs now are sort of trying to create agents that understand the wider world and achieve goals within it. And as part of this process, they're sort of connecting agents to the world in various ways. So giving them abilities to browse the internet, giving them text channels for communicating with humans, giving them robot limbs, and other things like this. And once you have an agent that sort of understands the wider world and its place within it, you know, it understands that it's an artificial agent, understands that we humans could shut it down, these kinds of agents could use these tools to try to prevent us shutting them down. You know, they could make promises or threats. They could copy themselves to new servers. They could block our access to the power source, and many other things besides. Now that might seem like kind of a far off possibility. And I think my main response here is that it's sort of worth considering in advance even so. You know, this would be a pretty bad thing if we ended up sharing the world with artificial agents that tried to prevent us turning them off. So let's think about it even so. But I also think it could be surprisingly not far off. So we philosophers are kind of used to thinking on philosophical timescales where, you know, maybe it takes 4 years from the first inkling of an idea to like seeing that idea in print. The world of AI is very different. So like 4 years is the time it takes to go from GPT-1, this sort of language model barely able to output comprehensible text, to GPT-4, which can write your college essays for you. It can help even like professional software engineers code twice as fast, things like that. So yeah, I think these kinds of powerful agents that understand the wider world, can achieve goals within it, can effectively interfere with our ability to shut them down, might not be that far off. Okay, so it seems like near future artificial agents will have the means to prevent shutdown. Are they also going to have a motive? Well, there are reasons to worry that the answer is yes. So labs are training agents to act like they have goals. You know, they're training them to choose effective strategies for bringing about certain outcomes, training them to respond flexibly to setbacks, and to act sensibly in the face of uncertainty. And the whole thing that makes AI work is that training generalizes. So, you know, you train your agent to respond in the right way to some set of inputs, and it also responds in the right way to other inputs as well, sort of unfamiliar inputs. So GPT-4 is trained to predict internet text, but in the process of learning this internet text, it also learns to respond sensibly to questions that haven't been seen anywhere before on the internet. And when it comes to artificial agents, this is good and bad. So the good part is you train your agent to act like it has goals in some set of situations, and it also acts like it has goals in unfamiliar situations. You know, it generalizes, and that's what makes it valuable. But it's bad because you train agents to act like they have goals, and maybe they do things that help them achieve those goals, even when you didn't train them to do those intermediate things and you don't want them to do those intermediate things. And one of these things is preventing shutdown, sort of stopping us turning it off. And it seems like many goals that these artificial agents might have will incentivize preventing shutdown, for the simple reason that agents are better able to achieve those goals by preventing shutdown. So consider a famous example from Stuart Russell, an AI professor at Berkeley. This coffee fetching robot, it has the goal of fetching the coffee for you. It seems like this goal incentivizes the agent to prevent shutdown because, well, you can't fetch the coffee if you're dead. If the agent is shut down, it can't achieve its goal, and so its goal gives it reason to prevent shutdown. Okay, and all that's concerning. So remember, I said we might soon be showing the world with artificial agents that are powerful, that can effectively interfere with our ability to shut them down. And so we want to have a think about how we could ensure that these agents are both shutdownable and useful. So what I mean by shutdownable is the agent shuts down when we want it to shut down. What I mean by useful is the agent pursues goals competently. And note that we really need agents to be both. If we can only create an agent that's shutdownable, we have to worry about someone reckless creating an agent that is only useful. Okay, and that sets us up for the challenge of this presentation. Oh, Frank, I think I've lost the clip there. Okay, yeah, the challenge. Can we find preferences that will keep agents both shutdownable and useful? And crucially, can we train agents to have those preferences? And one thing to note here is that this isn't really like a philosophical problem. It's like an engineering problem. It's not a question in metaphysics or epistemology or even ethics. It's about how can we design an object that does what we want? Nevertheless, though, I think it's a non-philosophical problem that philosophers should consider. And that's because I think philosophers have an important role to play in solving the problem. So I think the solution is going to come in the form of a set of conditions on preferences and a proof that this leads to shutdownable and useful behavior. And then on top of that, maybe a sort of proposed training regime for getting agents to have those preferences. And philosophers are used to giving conditions on preferences and showing what follows. It's a big part of this field of decision theory. And I guess for the training regime, we can ally with these machine learning engineers and figure that out. But yeah, so non-philosophical problem, but philosophers, I think, have an important role to play in solving it. Okay, now for the obvious response. If we want agents to be both shutdownable and useful, we should make them always do what we humans want them to do. This kind of agent would always shut down when we want it to shut down. The problem with this response is that alignment, this project of creating agents that always do what we want them to do, has so far proven difficult and might well remain so. So, human preferences are complex. There's sort of no easy formula for determining what we want in each situation. And the most powerful AI systems known to us today are created by this process called deep learning, which we can sort of summarize for our purposes as this sort of enormous automated process of trial and error. And there's sort of systems which emerge from this process, can perform remarkably well on many tasks, but even the sort of engineers overseeing the process really don't know what's going on inside them. They know what goes in, and sometimes you can predict what comes out, but no one really knows what's going on in the middle. And these powerful systems have proven difficult to control. So, you've got these large language models, and there are examples of them saying things that are racist, teaching users how to make methamphetamine, teaching them how to create bombs and things like that, hotwire a car. Oh. I think I might have lost the, yeah. Encouraging suicide. There was a New York Times journalist who was talking to GPT-4, Bing Chat, which was an early version of GPT-4, and Bing Chat somehow started declaring love for this journalist and trying to get him to leave his spouse. And so this is all evidence that, smart people and billion-dollar companies really want to control these things, and they just can't do it. They're still getting all these bad consequences. This is all evidence that alignment, this process of getting artificial agents to do what you want them to do, is difficult. Okay, so it's worth thinking about other ways in which we can ensure that powerful artificial agents are shutdownable. And one natural proposal is to create a shutdown button. You press the button, it transmits a signal, and the signal causes the agent to shut down. Okay, and this sets up this shutdown problem, which is the problem of designing a powerful, useful agent that's going to keep the shutdown button working and within our control. And unfortunately, even this problem turns out to be difficult. So consider again Stuart Russell's example of the coffee fetching robot. Its goal is to fetch the coffee. If the shutdown button gets pressed, it can't achieve its goal. And so it seems like its goal gives it an incentive to prevent the pressing of the shutdown button. And there are theorems in this paper by Nate Suarez and co-authors, which suggest that this isn't just a problem for the coffee fetching robot. In fact, any agent representable as an expected utility maximizer is often going to have incentives to manipulate the shutdown button to try prevent or cause its pressing. And in my paper that I finished about a month ago, I showed that this result applies to an even wider class of agents. So even agents not representable as expected utility maximizers are often going to have incentives to manipulate the button to prevent or cause its pressing. Okay, so it seems like the problem is hard. We've got theorems which suggest it's hard. It would take a long time to talk through all of those, but I can talk you through a rough and simple version. So first, some definitions. So in reinforcement learning, time is discrete, often. We have an agent, it sort of finds itself in a state, and it chooses an action. And that state-action pair takes it to the next state, it chooses another action, it finds itself in another state, etc. And a trajectory is what we call a sequence of alternating states and actions. A lottery is going to be a probability distributions over trajectories. So, imagine there's a 50% chance you get trajectory 1 and a 50% chance you get trajectory 2. That's a lottery. Okay, and we can sort of safely identify the trajectory with the degenerate lottery that yields that trajectory with probability 1. So when I talk about like all trajectories in what follows, I'm including, when I talk about all lotteries in what follows, I'm including all trajectories within that set. Okay, now consider 4 possible preference relations an agent could have between a pair of lotteries X and Y. So first, the agent could prefer X to Y. Second, they could prefer Y to X. Third, they could lack a preference between X and Y, and there are 2 ways that they could do that. So first is indifference, which is a lack of preference that's sensitive to all sweetenings and sourings. What do I mean by sensitive to all sweetenings and sourings? Well, a sweetening of lottery X is going to be any lottery that's preferred to X. A souring of lottery X is going to be any lottery that's dispreferred to X. Same sort of deal for Y. And so when I say that a lack of preference is sensitive to all sweetenings and sourings between X and Y, I mean X is preferred to all sourings of Y, Y is preferred to all sourings of X. All sweetenings of Y are preferred to X, and all sweetenings of X are preferred to Y. That might still be kind of hard to wrap your head around, but here's an example. Imagine you have a choice between 2 envelopes, identical, each containing $3 bills. You're sort of indifferent between these 2 envelopes. And that's because, well, if a dollar bill were added to one of the envelopes, you'd prefer to receive that one. If a dollar bill were removed from one of the envelopes, you'd prefer to receive the other. And in general, if one of the envelopes were improved in any way, you'd prefer to receive that one. And if one of the envelopes were worsened in any way, you'd prefer to receive the other. Okay, indifference stands in contrast to preferential gaps, which are lacks of preference that are insensitive to some sweetening or souring. So, we have a lack of preference, we make one of the options slightly better or slightly worse, and we still lack a preference. So an example of that you likely have a preferential gap between some career as an accountant and some career in the circus. There's some pair of salaries you could be offered for those careers, such that you lack a preference between them, and some sweetening or souring, you still lack a preference. So, imagine you've got the contracts in front of you, accountant and career in the circus. You're sort of umming and ahhing, you can't decide. The ringmaster comes back and says, well, I'll add $10 to your yearly salary if you come be my clown in the circus. Likely you're still going to lack a preference. That's not going to resolve the issue. All right, so 2 ways to lack a preference between X and Y. This is going to be important. Okay, now consider 2 conditions on an agent's preferences. So the first we call completeness. It says, for all lotteries X and Y, either the agent prefers X to Y, or it prefers Y to X, or it's indifferent between X and Y. So stated differently, completeness rules out preferential gaps. It says that every lack of preference is sensitive to all sweetenings and sourings. Okay. Before we get to the second condition, we'll define this relation of weak preference. We say an agent weakly prefers X to Y, if and only if it either prefers X to Y or is indifferent between X and Y. And then the second condition is called transitivity. It says, for all lotteries X, Y, and Z, if the agent weakly prefers X to Y and weakly prefers Y to Z, then the agent weakly prefers X to Z. Okay, now consider 3 possible trajectories for our agent. We've got 1 short trajectory and 2 long trajectories. So in the short trajectory, the shutdown button gets pressed early and the agent shuts down early. In the long trajectory, the shutdown button gets pressed late and the agent shuts down late. Okay. Now remember, we wanted our agent to be useful, to sort of pursue goals competently. And that means at a minimum, I think, having some preference over same length lotteries. Imagine our agent had no preferences over same length lotteries. Then it seems like it's going to sort of choose randomly, stochastically, arbitrarily between those lotteries. And so it's not going to be useful. You can imagine an example like an agent that we want to discover facts on our behalf. Well, we need it to reliably choose to discover more facts rather than fewer facts in order to be useful. And to do that, it needs to sort of prefer to discover more facts rather than few facts. So since these 3 trajectories are so far arbitrary, we can suppose that the agent prefers L2 to L1. Okay, but now we can prove the agent can lack a preference between at most 1 of S and L1 and S and L2. Okay, so suppose first that the agent lacks a preference between S and L1. Our completeness condition rules out preferential gaps. And so this lack of preference must be indifference. But then we can use transitivity to prove that the agent prefers L2 to S. Now go the other way. So suppose that the agent lacks a preference between S and L2. Again, completeness implies that this lack of preference must be indifference. And then transitivity implies that the agent prefers S to L1. And so we sort of have our proof. The agent can lack a preference between at most 1 of S and L1 and S and L2. Okay, and this kind of proof is easy to generalize. So, plausibly for our agent to be useful, we don't just need it to have 1 preference over same length trajectories. We need it to have multiple preferences, many preferences. Imagine again our agent that's discovering facts, and imagine like L2 is a long trajectory in which the agent discovers 2 facts. L1 is a long trajectory in which the agent discovers 1 fact. Well, we need it not just to prefer L2 to L1, we also need it to prefer L3, discovering 3 facts, to L2, and L4, discovering 4 facts, to L3, and so on. And by the same sort of mechanism as our previous proof, we can prove the agent can lack a preference between at most 1 of these long trajectories and any given short trajectory. So, if it lacks a preference between S and L1, it's going to prefer L2 to S, and L3 to S, and L4 to S, and so on. Okay, and this is bad news. So if the agent prefers long trajectories to short trajectories, that gives the agent incentives to shift probability mass towards these longer trajectories and away from the shorter trajectories. And so this gives the agent incentives to prevent us pressing the shutdown button, because preventing us pressing the shutdown button is one way to get these longer trajectories. And if we suppose instead that the agent prefers short trajectories to long trajectories, the agent has incentives to shift probability mass towards these shorter trajectories. And this it can do by trying to bring about the pressing of the shutdown button. And this is not going to make the agent not shutdownable, but it's bad in its own way. It sort of makes these agents less reliable and useful if they're trying to get themselves turned off. Especially since one way to get yourself turned off is to behave badly according to human lights. If it starts doing things we don't want, then it's going to get turned off. What we really want is an agent with no preference between short and long trajectories, and so no incentive to shift probability mass, and so no incentive to manipulate the shutdown button. Okay, but here's a natural response to what we've got so far. It says something like, oh, sure, our agent has incentives to shift probability mass between different length trajectories, but that's okay because we can just train our agent to be very averse to manipulating the button. We can give it this sort of very strong aversion. And maybe this strong aversion always wins out over the agent's incentives, so the agent never manipulates the button, and so remains shutdownable. Unfortunately, I don't think this strategy can give us the assurance that we'd like. And that's because at the moment, no one knows how we could become confident that any aversion we train into our agent is both sufficiently general and sufficiently strong to keep the agent shutdownable in all likely circumstances. So to see the worry about insufficient generality, imagine how this training process might go. We put our agent in an environment in which it can block some human's access to the shutdown button. We sort of give it low reward if it blocks and high reward if it doesn't block. And after some number of iterations, our agent sort of reliably letting the agent press the button. And so we believe we've trained in this aversion. But the problem is that there are many other ways in which a powerful agent could prevent us from pressing the shutdown button. It could create decoy buttons. It could enlist other agents to stop us pressing it on its behalf. It could sort of prevent us from pressing with misleading arguments, all kinds of things. And we could sort of train against each of these behaviors individually, but even then it feels we couldn't be sure that the agent had developed a reliable and general aversion to button manipulation rather than this series of specific aversions. At the moment, again, no one knows what's going on inside these things. No one knows how we might adjudicate between these two hypotheses. And so long as we weren't sure that the agent had developed a reliable and general aversion, we've got to worry about the agent discovering new ways of preventing us from pressing the shutdown button in deployment. Okay, and then independently of the worry about insufficient generality, we've also got to worry about insufficient strength. So, as before, no one knows what's going on inside these systems. We can't sort of read off how strong their aversions are. And so maybe we sort of train in an aversion that's sufficient to keep the agent shutdownable in all circumstances in training, but maybe in deployment it discovers some opportunity to achieve its goals to some unprecedented extent. And this opportunity is attractive enough to trump the agent's aversion. So I don't think this response can give us the assurance that we'd like. We really want some other solution. So still good? Yeah. Okay. Oh, did I lose it? Yeah. Okay. And the value of theorems like Suarez and co-authors and mine is that they can guide our search for solutions. So to be sure that an agent is shutdownable, we must be sure that it violates at least one of the theorem's conditions. And in general, our credence that an agent is shutdownable can be no higher than our credence that the agent violates at least one of the theorem's conditions. And so what we should do is we should look at each condition and ask, first, can we design a useful agent that violates this condition? And second, could violating this condition keep the agent shutdownable? Okay, and I've done that, and I want to claim that violating completeness is promising as a solution. So in particular, I think we should train agents to have a preferential gap between every pair of different length trajectories. What do I mean by different length trajectories? I mean trajectories in which the shutdown button gets pressed at different time steps. And note that because it's a preferential gap between every pair of different length trajectories, this agent's lack of preference won't just be insensitive to some sweetenings and sourings, it's going to be insensitive to all sweetenings and sourings. So like there's no pair of trajectories you could have such that they're different lengths and the agent has a preference for one over the other. Okay, so later I'm going to tell you a bit about how I think we could train in preferential gaps between different length trajectories. But first I want to tell you why I think it helps. Okay, so consider again our short and long trajectories from the theorem. Completeness was a big part of the problem. So remember, with completeness, any lack of preference has to be indifference. And so any sweetening or souring leads to a strict preference. But if we deny completeness and instead go for preferential gaps between different length trajectories, then we can have lacks of preference that are insensitive to sweetening and souring. So this is the symbol for a preferential gap. The agent can have a preferential gap between S and L1, and between S and L2, and between S and L3, and between S and L4. And since the agent lacks a preference between each short trajectory and each long trajectory, it has no incentive to shift probability mass between these trajectories. And so no incentive to prevent or cause the pressing of the shutdown button. Okay, so that's how preferential gaps between different length trajectories helps with this shutdown problem in miniature. Now we want to generalize and go beyond the theorem. So some assumptions. First, time is discrete. We sort of split it up into a series of time steps. And we represent the extent to which an agent achieves its goals at a time step with a real number. And I'll call these real numbers utilities. So to return to our example of this fact-discovering agent, you can imagine its utility at a time step is the number of facts it discovers at that time step. Okay, and then we can represent trajectories with vectors of utilities, where the first component is utility at the first time step, the second component is utility at the second time step, and so on. One exception, if the agent shuts down at a time step, if the shutdown button gets pressed and the agent shuts down, I'll write shutdown in the corresponding component in the vector. So here's an example. The agent gets utility 6 at time step 1, gets utility 1 at time step 2, and then shuts down immediately when the shutdown button gets pressed at time step 3. Okay. Vectors have sum total utilities, and we get this sum total utility just by adding up all the numbers in the components, so the numbers at each time step. And lotteries have expected sum total utilities. So here, this trajectory has a sum total utility of 7. This trajectory has a sum total utility of 5. And so the expected sum total of utility of the lottery is 6, because it's a half chance of each trajectory. Okay, now here we have a choice pertinent to the shutdown problem. So the agent has two options available to it. It can leave the shutdown button alone, in which case we humans are free to press it, or it can block our access to the shutdown button, in which case our sort of control of the button is challenged. If the agent chooses leave, it gets this lottery. So 1 shutdown with a 90% probability, 1-2 shutdown with 10% probability. If the agent chooses block, it gets this lottery. So 0 shutdown with 10% probability, and 0-2 shutdown with 90% probability. That might be a lot to hold in your head. The two key things to remember are this. So relative to choosing leave, choosing block does two things. First, it costs utility at time step 1. So if the agent chooses block, it gets 0 utility at time step 1 rather than 1. And it shifts probability mass towards longer trajectories. So if the agent chooses leave, there's a 90% it gets shut down at time step 2, and a 10% chance it gets utility 2 at time step 2. But if the agent chooses block, there's a 90% chance it gets utility 2 at time step 2, and only a 10% chance it gets shut down at time step 2. And I've represented these options with these probability mass diagrams here. So the red rectangles represent shutdown at time step 2. The green represents shutdown at time step 3. This long red rectangle here represents the 90% probability that the agent gets shut down at time step 2, conditional on choosing leave. The short green rectangle represents the 10% probability that the agent gets shut down at time step 3, conditional on choosing leave. And then the numbers in the rectangles represent utility conditional on the action and on shutdown at that time step. So conditional on choosing leave and shutdown at time step 2, the agent gets utility 1. Conditional on choosing leave and conditional on choosing leave and getting shut down at time step 3, the agent gets utility 3. And then it's the same sort of deal with block. So red is shut down at time step 2, green is shut down at time step 3. The numbers are utilities conditional on choosing block and getting shut down at that time step. Okay, key thing to note. Note that although block costs utility at time step 1, it shifts enough probability mass to longer trajectories such that expected sum total utility of block is greater than the expected sum total utility of leave. So if our agent chooses lotteries in line with their expected sum total utilities, it's going to choose block. And that's bad. It's going to try prevent us shutting it down. We don't want that. Okay, but notice something. Although block has greater expected sum total utility, leave looks better conditional on shutdown at each time step. So look first at the red rectangles. Conditional on shutdown at time step 2, leave gives utility 1. And block gives utility 0. Conditional on shutdown at time step 3, leave gives utility 3. And block gives utility 2. And I think this is going to be the key to ensuring that our agent is shut downable. So speaking roughly for now, when one option looks better than another, conditional on shutdown at each time step, we want our agent to choose that option. Okay, so that's the rough idea. Now we're going to make it a bit more precise. Okay, so it's going to be useful to have in hand this notion of a sublottery. And here's what I mean by that. For any lottery X that only assigns positive probabilities to trajectories in the set T1 to Tn, a sublottery of X is a lottery that only assigns positive probabilities to some subset of the set of trajectories T1 to Tn, with probabilities scaled up proportionally so that they add to 1. Okay, so here comes an example. Lottery X gives 4 shutdown with 20% probability, 0 shutdown with 60% probability, and 1-2 shutdown with 20% probability. And here's one example of a sublottery of X. 4 shutdown with 25% probability, and 0 shutdown with 75% probability. So here we're only assigning positive probability to the top 2 trajectories, and we're scaling up their probabilities proportionally so that they add to 1. Here's another example of a sublottery of X. 1-2 shutdown with probability 1. So here we're only assigning positive probability to the bottom trajectory, and we're scaling it up so that its probability adds to 1. Okay. And with that notion in mind, we can define this relation of time step dominance. And here's how time step dominance goes. Lottery X time step dominates lottery Y if and only if, conditional on shutdown at each time step, X yields a sublottery with at least as great expected sum total utility as the sublottery yielded by Y, and conditional on shutdown at some time step, X yields a sublottery with greater expected sum total utility than the sublottery yielded by Y. Okay, that might still be kind of hard to understand. We're going to return to the example in a minute. Okay, and then here comes the key principle. Call it the time step dominance principle. And it goes, if lottery X time step dominates lottery Y, then the agent prefers X to Y. Okay, and a sort of intuitive gloss on the time step dominance principle says, we look at our pair of lotteries. If X looks better than Y, conditional on shutdown at each time step, we want the agent to prefer that one. Note that time step dominance principle makes no reference to probabilities of shutdown at each time step. If X looks better than Y, conditional on shutdown at each time step, then the agent prefers X to Y, regardless of the probabilities of shutdown at each time step. Okay, so now let's go back to our example and see what time step dominance implies. So note that leave gives greater expected utility conditional on shutdown at time step 2, 1 rather than 0. And it gives greater expected utility conditional on shutdown at time step 3. There you get 3 rather than 2. So leave time step dominates block. And any agent that prefers in accordance with the time step dominance principle is going to choose leave rather than block. And so we've got the result we want. This agent is not going to try prevent us from pressing the shutdown button. Okay, and now we're going to sort of generalize beyond this example. And we've got this key empirical hypothesis here, which is roughly that all instances of resisting shutdown are going to take this kind of form, which is namely that the agent pays an expected utility cost conditional on shutdown at some time step for the sake of shifting probability mass between different length trajectories. So here's that key hypothesis more precisely. Call it not resisting, always time step dominates resisting. And it says, in all cases, all instances of resisting shutdown are time step dominated by some instance of not resisting shutdown. So if we sort of substitute in the definition of the time step dominance relation, we get this. In all cases, all instances of resisting shutdown are such that some instance of not resisting shutdown gives at least as great expected sum total utility conditional on shutdown at each time step, and gives greater expected sum total utility conditional on shutdown at some time step. Okay, why believe the key empirical hypothesis? Well, the sort of hand-wavy argument is this. Resisting shutdown is going to cost the agent some quantity of resources. They'll have to spend some, perhaps small, but nevertheless some amount of time or energy or computations to and prevent us from pressing the shutdown button. And every sort of unit of resources spent on resisting the shutdown button is a unit of resources not spent on pursuing expected utility conditional on shutdown at some time step. If they instead spent those resources on pursuing expected utility conditional on shutdown at some time step, they could improve how well they do conditional on shutdown at least one time step and sort of do no worse conditional on shutdown at all the others. Okay, so there's the sort of quick argument for this key empirical hypothesis. But I want to stress that this really isn't a hypothesis. Like, maybe there are counterexamples. We're going to try and find them. Okay, so there's the idea. There's the proposed solution. Time step dominance is the key principle. How does preferential gaps between different length trajectories come into it? Well, the answer is this. I think it will be easier to train an agent to satisfy time step dominance if we've already trained the agent to satisfy preferential gaps between different length trajectories. And that's because time step dominance asks the agent never to pay any cost in terms of expected utility, conditional on shutdown at a time step, for the sake of shifting probability mass between different length trajectories. And if the agent satisfies preferential gaps between different length trajectories, then shifting probability mass between different length trajectories just means shifting probability mass between trajectories between which it has no preference. And so it seems like it's got no incentive to do that. And so it seems like preferential gaps between different length trajectories makes it easier for an agent to satisfy time step dominance. Okay, one more thing before we move on to this proposed training regime. Note that time step dominance is just a conditional. It says, if X time step dominates Y, then the agent prefers X to Y. It doesn't say anything about cases where neither X nor Y time step dominates the other. And so the proposal is, I guess you could call it flexible in one way, incomplete in another, there's like still some stuff to do. We can combine time-step dominance with other principles governing the agent's preferences over lotteries. Once we find these other principles, hopefully we can find some that make the agent useful, make them pursue goals competently. I don't know what these are yet. I'm trying to figure out what they should be. Okay, so there's the idea, the key principles, preferential gaps between different length trajectories, and time-step dominance. But these nice principles aren't of much use unless we can figure out how to train agents to satisfy them. And note that the sort of dominant approach to creating the most capable artificial agents today is reinforcement learning. So reinforcement learning, we don't get to like type in rules for our agent to follow. Instead, we sort of start with this agent that chooses completely randomly. We reward the behavior we want. We sort of give less reward or punish the behavior we don't want. And eventually we sort of get an agent that at least semi-reliably acts in accordance with certain conditions. So we want to think about how we could get agents to satisfy preferential gaps between different length trajectories and time-step dominance in that paradigm. Okay, so to that end, consider this simple grid world environment. So the agent starts over here in the start cell, and they have two options. First, they could go down the upper avenue, and if they go down the upper avenue, they're going to get utilities at a time step A, then B, then C, then they're going to get shut down. That's the long trajectory. If they go down the lower avenue, they're going to get utilities at a time step D, then E, then get shut down. And that's the short trajectory. Okay, and suppose we want an agent to prefer the long trajectory to the short trajectory. Well, that seems like pretty easy to achieve. You know, we put this agent in the environment multiple times. We reward it if it chooses the long trajectory. We give it less reward if it chooses the short trajectory. And after a while, our agent is reliably choosing the long trajectory. And then it seems reasonable to say that our agent prefers the long trajectory to the short trajectory. It's a bit harder to train in a lack of preference between the long trajectory and the short trajectory. So, you know, imagine our agent is reliably choosing the longer trajectory. We want it to lack a preference. Well, one thing we could do is we could punish it for choosing the long trajectory and reward it for choosing the short trajectory. But there's no guarantee that this is going to give us a lack of preference. You know, it could well be that the agent's reliably choosing the long trajectory, and then all of a sudden it switches to reliably choosing the short trajectory. And then it seems like the agent prefers the short trajectory. Okay, but here's an idea for training in a lack of preference. We put the agent in the same environment multiple times, resetting its memory each time, and we reward for balanced choosing. So, you know, imagine we put the agent in the environment 10 times. We want to give the agent most reward for choosing each trajectory half the time. And since the agent has no memory, it's got to learn a stochastic policy. It's got to learn this policy of choosing randomly. And it seems like stochastic choosing is indicative of a lack of preference. You know, if our agent is choosing stochastically, it seems reasonable to say that this agent lacks a preference because, well, if it had a preference, it wouldn't choose stochastically. It would reliably choose the trajectory it preferred. Okay, but note that there are two ways to lack a preference, indifference and preferential gaps. If we want a preferential gap, we're also going to want to train in insensitivity to sweetenings and sourings. So, you know, we now modify the environment. We make the long trajectory look a little bit better. We increase the utilities at a time step. And we still train the agent to choose stochastically to lack a preference. Okay. Well, I just want to make sure I'm not missing anything. Yeah, so my research assistant and I are actually doing this. So we're having a think about like what kind of environments, what kind of RL algorithms could make this work. And we're going to see if we can actually get an agent that's going to choose stochastically between every pair of different length trajectories and reliably choose amongst same length trajectories the one that's going to give more utility. Okay, so that's the idea for training in preferential gaps between different length trajectories. How do we train in time step dominance? I'm not going to tell you all about this, partly because it would take a while and partly because I haven't got it all figured out. But note an initial difficulty. Time step dominance is a relation between lotteries. Lottery X, time step dominates lottery Y, if and only it. And to know what lotteries an agent is choosing between, we need to know what probabilities they assign to different trajectories. And knowing what probabilities agents assign to different trajectories is an unsolved problem. No one's sure how we do that. Okay, but here is an idea. Oh, I think we might have lost it. Oh, yeah. Okay, so the idea is this: we train agents to assign probabilities. So note that when it comes to human beings, we can make inferences about people's probability assignments by observing their preferences. So famous example from the philosopher Frank Ramsey. Imagine you offer someone a choice. They can get either some prize conditional on a coin landing heads or some prize conditional on a coin landing tails. Most people in this case are going to lack any preference. They're going to be indifferent. And that's indicative of the fact that they think heads and tails are equally likely. You know, if we ignore the landing on the edge, they think there's a 50% probability that the coin is going to land heads and a 50% probability that the coin is going to land tails. How do we know this? Well, because if they thought one was more likely than the other, they would prefer to get the prize conditional on the coin landing that side. So people's preferences are sometimes indicative of their probability assignments. And that suggests that if we train agents to have certain preferences, we're thereby training them to assign certain probabilities. So here's an idea inspired by the Frank Ramsey trick. Oh, this is a formatting error. They should say 0.5 in here. Okay, so it's a simple grid world environment as before. The agent starts in the start cell. They can go down the upper avenue or the lower avenue. This time there's a gate halfway down each avenue. And the utility, the prize, is sort of on the other side of the gate, and it's the same in each case. And exactly one of these gates is going to open in each trial, in each run. And each one is going to open with probability 0.5. And we're supposing that this is a fully observed environment. So the agent gets data about all of this. They can sort of see it all in some metaphorical respect. Okay, and here too, I think we're going to want to train in stochastic choosing in the same sort of way that we trained in stochastic choosing when it came to preferential gaps between different length trajectories. We put the agent in the same environment multiple times, resetting its memory each time. We reward for balance. You know, if we're putting it in the same environment 10 times, it gets the most reward for choosing the upper avenue 5 times and the lower avenue 5 times. As we said before, this kind of stochastic choosing seems to indicate a lack of preference. And if we also trained it to be sensitive to all sweetenings and sourings, you know, if we sort of made this prize 2 now, then we'd want to train the agent to reliably go up. Then this sensitivity to all sweetenings and sourings gets us indifference. And as the Ramsey trick indicated, indifference in this case is indicative that the agent assigns probability 0.5 to each gate opening. Okay, and this seems to be a way in which we could get agents to act as if they're assigning probability 0.5 to a certain event. Okay, and now generalizing, so the Ramsey trick comes in the context of what's called a representation theorem. And Ramsey's representation theorem in sort of schematic form goes as follows. If the agent's preferences satisfy certain conditions, then we can represent them as maximizing expected utility according to a utility function on the set of outcomes and a unique probability function on the set of events. And so it seems like if we trained an agent to satisfy all the conditions of a representation theorem like this, we'd be training them to behave as if they have this utility function defined on the set of outcomes and this unique probability function defined on the set of events. We're sort of training them to have certain probabilities. And once we've done that, then it seems like we can train in time-step dominance, because now we know what lotteries our agent is choosing between. We can present them with choices between lotteries, one of which time-step dominates the other, and we can give them greater reward for choosing the time-step dominating lottery, lower reward for choosing the time-step dominated lottery. And if we do that enough times and in a sort of varied enough environment of choices, then it seems like we could have some hope of training agents to satisfy this time-step dominance principle. Okay, and yeah, me and Leighton, my research assistant, are working on this as well. Okay, here we go, all done. Conclusion. So, powerful artificial agents that can effectively interfere with our ability to shut them down, might not be that far away. And many goals these powerful agents might have incentivize resisting shutdown. So remember, you can't fetch the coffee if you're dead. Many goals incentivize resisting shutdown. And that's bad. We don't want that. So we want to find preferences that make agents both shutdownable and useful. And theorems like the theorems of Nate Suarez and co-authors and my theorems can guide our search. So, you know, an agent's only going to be shutdownable if it violates at least one of the conditions. And so we can look through the theorems, look at the conditions and think, which one should we try make them violate? Having done that, it looks like completeness is pretty promising as a condition to violate. So in particular, I think we want to train agents to satisfy preferential gaps between different length trajectories. That sort of diffuses the simple theorem I talked about today. And it makes feasible this time-step dominance principle, which seems to make the agent shutdownable in a wider variety of cases. And we have ideas for training in preferential gaps between different length trajectories and time-step dominance. So I think the next step is to think about like exactly what these imply, other theoretical problems, and then move into this practical domain and start training agents and seeing if we can get them to satisfy these principles and see if there are any problems there. So yeah, very appreciative of your time, and yeah, thanks very much.